In this video, I'm going to show you how to use the Hückel MO routine to calculate the pi orbital systems of conjugated molecules. So we're going to start here with about the simplest molecule you can have of a pi bond, which is ethylene. And ethylene, of course, you know, has a pi and a pi star system. Well, Oscar can show you that pi system by going down here, clicking that the Hückel MO system is turned on, and then you do auto select. What auto select does, it finds all the orbitals in the pi system of the molecule. And so here we have ethylene, and what ethylene, of course, has is a pi bond and a pi star bond. And over here on the right-hand side, you'll see two orbitals. The lower one has a pair of electrons in it. That represents the pi bond. That's the one that's shown. And then this one up here at top is the antibonding orbital. Now these are the energies on the left. The beta units are absolutely arbitrary, and it shows the degree of bonding. So bonding orbitals actually have positive values. They're down in the hole. Basically, you can think of this as the depth of the hole. Actually, what it really means is a beta is a negative number of energy. So where the depth of a hole is 1 beta, and the antibonding is up here at negative beta. Now we can see the antibonding orbital by going down here and clicking the up arrow here, and now you see the box moved up here. This is now the empty orbital of ethylene. Now if that was all there was to it, we wouldn't need a program, but the fun comes in is when we make the molecule longer. So let me turn the Hückel off for a second, and actually turn both of them off, and we'll go to butadiene. We'll make the molecule longer. So here's butadiene. I didn't actually have to turn the Hückel off to do that, but I just wanted you to see what was happening a little bit better. So here now is butadiene, and in butadiene, of course, we now have 4 orbitals. Now it's still selected for the first antibonding orbital. So let's go down. So here's the lowest orbital. All the signs are positive. You can see there's no nodes along here. Everything's in phase. We can go up one level. Now we can see the antibonding orbital. This is an antibonding between carbons 2 and 3. It's still bonding between 1 and 2 and 3 and 4. So it means that the orbital is net bonding. We go to the first totally antibonding orbital up number 3, and now it has 2 nodes, node here, node there, and then we go to the top one, and of course it's now this one's totally antibonding as it alternates. Notice, of course, that the coefficients of the atoms in the MO are not all the same, and this is just the way MOs work. Is that they act like waves, and the waves, of course, have various ups and downs as you go through the system, and they'll have different magnitudes. So let's make it 1 atom longer. Okay, so I'm going to add, of course, I just added a methyl group there. But how could we make that 1 atom longer in a more meaningful way? Well, what if it had a charge? What if it were actually a cation? So now what I've done is I've spread these 4 electrons, because I've added a cation. I didn't add any more electrons. I spread 4 electrons over 5 centers, and so now you see 5 MOs. And the one in the middle, which let me select the one in the middle, actually is essentially non-bonding. That's why it's in the middle. See, there's no adjacent coefficients there. And so in terms of resonance structures, this would be corresponding to drawing resonance structures where you move this positive charge from the end atom to the middle atom to the other end of the molecule. There's no coefficients on carbons 2 and 4. So that's kind of interesting. Well, let's go. Let me get rid of that charge. Okay, and I'm going to go on to an anion. So I'm adding in 2 electrons. So now it's an anion, and of course now we fill that middle orbital there. And so if we go back to that middle orbital, you'll see now the negative charge is on carbons 1, 3, and 5. So it makes sense. The negative charge is the same place where the positive charge was on the cation. So let's go on to a 6-atom system. So I'm just going to get rid of the negative charge temporarily here, and now I'm going to draw in 1 more double bond. And so now we have a 6-atom system. And in the 6-atom system, again, let me just go down to the bottom and start. here we start with a one of 0 nodes. We go up to orbital 2. We have 1 node down the middle. Okay. We go up 1 more. We have 2 nodes. There's 1 node there, 1 node there. Now we go to the first antibonding orbital, and there's 1 node there, 2 nodes there. There's a 3. The next one I should have 4 nodes. There's a node there, 1, 2, no node in the middle, 3, 4, and the one on top, of course, will be alternating every other orbital. So you can play these games as much as you like. Fun things happen is when we get to rings, because this is going to lead into what we call aromatic systems. So let me that's a 6-atom system here, but let me just add in, we're going to add in a benzene molecule. So now I have a second molecule on here at the same time. So let me do auto select, and I'm going to do something here. Notice how these things are hard to read. I'm going to click the circle here, and what this is going to do, instead of showing the orbitals from the side, it's going to show them from the top. This is still p orbitals, but we're looking at the molecule as if we were from above. And you can switch back and forth through these, but when you get complex things like benzene, it's better to look at the top view. So it just looks like a circle, but you should remember that this is really, you're looking at a p orbital end on. So to get to the benzene orbital, what we have to do is we have to go to system 2, because that was the second molecule drawn. And look at the difference between benzene with 3 double bonds in a ring versus the hexatriene with 3 double bonds in a row. The benzene ones, the orbitals come together and form pairs. This is because of the cyclic nature of the molecule, and it basically has to be this way. The reason it has to be this way is because benzene doesn't have a fixed coordinate system. All the atoms in benzene are the same. And so if you're going to draw a node through the molecule, you can't say it depends on which direction you draw the node. Because if we draw the node this way, that's no difference than drawing the node this way or that way, because the molecule has symmetry. And because of this symmetry, we get these paired up energy orbitals. These are called degenerate orbitals. So benzene has 3 bonding orbitals. The bottom one, I'll go down to the bottom one, has 0 nodes. The next 2 have 1 node. But the node can either be horizontal here, or it can be vertical. And actually, this is the way the program draws it. They could be turned at different angles as long as those 2 nodes are orthogonal to one another. And that's simply because the molecule doesn't have a built-in coordinate system. And now the antibonding orbitals, there's now a big gap. And if we go up here, we can see now there's 2 nodes, 1 node this way, 1 node that way, or 2 nodes drawn horizontally and vertical. So the 2 nodes are either like this, horizontal and vertical, or they're like this, turned toward the diagonal positions. And so this is the nature of a ring, and this gives benzene a special property, which we call aromaticity. Now, what does that aromaticity due to? Well, it's due to the fact that these things, when they pair up, they give you a much bigger gap between the highest occupied MO and the lowest unoccupied MO. And that gap means stability, because having a higher occupied orbital means the molecule is a better electron donor. Having a lower unoccupied orbital means it is a better electron acceptor. So benzene, compared to the hexatriene, is a poorer electron donor and a poorer electron acceptor. Let's go back to hexatriene for a second and see here, look how small the gap is. So this is a much better electron donor than benzene. It's a much better electron acceptor than benzene. Another way of saying it is hexatriene is a reactive molecule, whereas benzene, with this big gap, is a very stable molecule. So these cyclic molecules, if they meet the aromatic rule, can have very good stability. Now, just being cyclic doesn't necessarily mean you have this big gap between the homo-LUMO, because let's see what happens if I draw a 4-membered ring. So I'll do the 4-membered ring. Whoops, got to get my bond on here. Do a 4-membered ring. And so click, click. This is going to be system 3 now. And so look what happens. 4-membered ring, we get paired electrons, but they're right in the middle. So the homo-LUMO gap
It's zero. It's the molecule is non-bonding. It's got a pair of electrons and two orbitals. This is an extraordinarily reactive molecule. So this is not aromatic at all. And so you have to have, it turns out, there's this wonderful rule which says you have to have 4n plus 2 electrons. Well, the 4n is the key things. The 2 electrons count for the one on the bottom. And then as you go up, you need these things to occur of equal 4 electrons. So you get this nice big homo-lumo gap. So 6 works, 4 does not. And if we go, we have to go all the way up to 10 to find the next one that works. And you're going to talk about that more in lecture, of course. But this is the origin of that aromatic rule. So anyway, this is an introduction to using the Hückel program to calculate these conjugated MOs. Have fun with it. There are more things to it. You can use it to calculate charges. We can add hyperconjugation, but we'll talk about that in a separate video.